October 24th, 2025. Right now, as you're watching this, an object the size of Manhattan is moving through our solar system at 68 kilometers per second. And 3 days ago, scientists at the European Space Agency detected something that, according to every model we have, should not be possible. The trajectory changed, not drifted, not adjusted by solar wind or outgassing pressure. Changed, with a delta V signature that would require thrust, directed, sustained thrust, the kind you'd see from a spacecraft making a course correction, not a ball of ice following the laws of gravity. The data came through on October 21st at 1447 UTC. By October 22nd, 14 independent observatories had confirmed the same readings, and by October 23rd, NASA's Jet Propulsion Laboratory quietly updated their orbital elements for 3I Atlas, without any public statement explaining why the predicted path suddenly didn't match observations. The object that was supposed to pass 280 million kilometers from Earth in December is now projected to close that distance by 18 million kilometers. And the maneuver that created this change happened during the 8 days when 3I Atlas was hidden behind the Sun, unobservable from every telescope on Earth, at the exact moment its velocity peaked, executing what orbital mechanics specialists call the most fuel-efficient window for deep space navigation. If you're engineering a trajectory through an alien star system, this is exactly how you'd do it. The question isn't whether the trajectory is impossible anymore. The data is unambiguous. The question is, what changed it? What we're watching unfold isn't just another comet story. It's something that's forcing astronomers to recalculate everything they thought they understood about how objects move through space. And the timing, the precision, the sheer improbability of what happened during those 8 invisible days. It's creating conversations in observatories and research institutions that nobody expected to be having in 2025. Let me take you back to October 21st, 2025, 1447 UTC. That's the moment when everything changed, though most of the world didn't know it yet. A network of amateur astronomers, part of a collaborative tracking initiative that's been following 3I Atlas since its approach became visible in late September, noticed something in their data that made no sense. They were comparing their real-time positional measurements against the predictions published by NASA's Jet Propulsion Laboratory through the Horizon system, the gold standard for solar system object tracking. And the numbers didn't match. Not by a small margin that could be explained by measurement error or atmospheric distortion. By over 1 million kilometers. An object that was supposed to be at one specific coordinate in space was somewhere completely different. Now, you have to understand what this means. The JPL Horizon system doesn't just guess where objects are going to be. It calculates trajectories based on gravitational mechanics that have been refined over centuries, using the combined mass influences of the Sun, planets, and even large asteroids. These predictions are accurate to within kilometers for objects like comets and asteroids. When spacecraft navigate to Mars or rendezvous with comets, they rely on these same calculations. The system works. It's been tested thousands of times. So when independent observers started reporting that 3I Atlas was not where Horizon said it should be, the immediate assumption was that the observers were wrong. Bad calibration, software glitch, coordinate system confusion, something on their end. Except within hours, more observatories started confirming the same deviation. By the morning of October 22nd, professional facilities had joined the effort. The Observatorio Astronómico Nacional in Spain, the Siding Spring Observatory in Australia, the Haleakala Observatory in Hawaii, 14 independent facilities using different equipment, different software, different analysis methods, all reporting the same result. 3I Atlas was not following the predicted trajectory. The right ascension coordinate was off by 0.0047 degrees. The declination showed a deviation of 0.0029 degrees. Those sound like tiny numbers, but at the distance 3I Atlas was travelling from Earth at that moment, roughly 1.4 astronomical units, those angular offsets translated to positional errors exceeding 1.2 million kilometres, and it was growing. Every hour the discrepancy widened. By October 23rd, the deviation had increased to 1.8 million kilometres. Whatever had changed the object's path wasn't a one-time event, it was sustained, continuous. The trajectory was actively diverging from what gravitational mechanics alone would produce. So on October 23rd, quietly, with no press release, no public announcement, NASA's Jet Propulsion Laboratory updated the orbital elements for 3I Atlas in the Horizons database. New eccentricity value, new perihelion distance, new velocity vectors. The predictions suddenly matched observations again. But here's what they didn't explain: why the original predictions were wrong in the first place, or what physical mechanism could account for the change. Let me walk you through what this deviation actually represents in terms of physics. To change an object's trajectory by 18 million kilometers over the course of several weeks, which is the revised closest approach adjustment now being calculated for December, you need to alter its velocity, not just its position, but the speed and direction it's travelling. The relevant measurement here is called delta v, change in velocity, and based on the trajectory modifications observed, the delta v required would be somewhere in the range of 0.12 to 0.18 kilometers per second. That might not sound like much compared to the object's total velocity of 68 kilometers per second, but in terms of the energy required, it's enormous for a comet nucleus estimated to be between 8 and 12 kilometers in diameter, assuming average cometary density around 500 kilograms per cubic meter. We're talking about a mass somewhere in the range of 300 to 600 billion kilograms. To accelerate that mass by even 0.12 kilometers per second requires kinetic energy on the order of 2 to 6 trillion joules. That's the energy output of a large nuclear power plant running continuously for weeks, and it has to come from somewhere. In a natural comet, the only available energy source is outgassing, jets of sublimated ice and dust being expelled from the surface as the comet heats up near the sun. These jets can create thrust, and we've observed this with comets like Halley and 67P/Churyumov-Gerasimenko. It's called the rocket effect, and it's well documented. But here's the problem. The magnitude of thrust required to produce the observed trajectory change exceeds anything we've ever measured from cometary outgassing by at least 2 orders of magnitude. The most vigorous cometary jets we've studied produce accelerations around 0.00001 meters per second squared. To generate the delta V observed with 3I Atlas, you'd need sustained acceleration closer to 0.0001 meters per second squared, possibly higher, depending on the exact mass of the nucleus. That's 10 times more powerful than the most active jets ever recorded, and the direction of the thrust would have to be extraordinarily precise, not random venting, but directed in exactly the configuration needed to modify the trajectory in the specific way observed. There's another problem too. Outgassing produces visible coma and tail structures. The sublimated material creates a diffuse cloud around the nucleus that we can see and measure spectroscopically. With 3I Atlas, observers have noted that the coma is relatively modest for an object of its size at its current distance from the Sun. The brightness and extent of the coma don't correlate with the kind of vigorous outgassing that would be needed to produce this level of acceleration. It's like seeing an effect without the expected cause. The trajectory changed, but the physical evidence of the mechanism that should have changed it is insufficient. Now, I want to be very clear about something. These observations, these claims of trajectory deviation and insufficient outgassing, they're circulating primarily among independent observer networks and online astronomy communities. The professional institutions, NASA, ESA, the International Astronomical Union, they haven't made public statements confirming that the trajectory change is anomalous or unexplained. The JPL Horizons update could simply be a routine refinement as more observational data becomes available. Orbital predictions are updated frequently for newly discovered objects as we gather more measurements and improve the accuracy of the initial trajectory calculations. That's normal, expected, standard practice. But what's generating attention, what's causing astronomers to pay closer attention than usual, is the combination of factors. The timing of the deviation occurring during solar conjunction when the object was unobservable, the magnitude of the change exceeding typical refinement adjustments, the lack of proportional outgassing signatures, and most significantly, the revised trajectory that brings the object 18 million kilometers closer to Earth than originally predicted. That's still an enormous distance, more than 40 times the distance to the Moon, nowhere near threatening, but it's different. And in astronomy, when something behaves differently than predicted, we pay attention, not because it's necessarily extraordinary, but because it's informative. Anomalies teach us things. They reveal gaps in our models, factors we didn't account for, physics we didn't fully understand. So what we have right now, on October 24th, is an object that changed trajectory during a period when we couldn't observe it. using a mechanism that doesn't obviously match the visible outgassing activity, resulting in a path adjustment that required energy output at the high end of what natural comet processes should be able to produce. It's not impossible, it's not physics breaking, but it's unusual, and the fact that JPL quietly updated the orbital elements without explanation is what's keeping this story alive, because it suggests the deviation is real, not just observer error, but also not significant enough to warrant public clarification. That gap between official acknowledgement and public curiosity, that's where speculation grows. And right now, speculation is growing fast because the next question everyone's asking is what exactly happened during those 8 days when 3i Atlas was hidden behind the sun, and why that timing matters more than anyone initially realized. Between October 21st and October 29th, 2025, something happened that we cannot directly verify, and that lack of verification is precisely what makes it significant. For 8 days, 3i Atlas passed through solar conjunction, the period when an object's line of sight from Earth crosses directly behind the sun. During this window, the object becomes unobservable from ground-based telescopes and most space-based assets, because the overwhelming brightness of the sun drowns out any reflected light from the object itself. It's an observational blackout, a gap in the data, and in astronomy, gaps are where the most interesting things can hide. The conjunction began on October 21st, the same day the trajectory deviations were first detected, and it will end on October 29th when the object emerges from solar glare at perihelion, its closest approach to the Sun at 1.36 astronomical units, roughly 203 million kilometers from the solar surface. That's actually farther from the Sun than Earth's orbit, which sits at 1 astronomical unit. For context, Mars orbits at about 1.5 astronomical units, so 3i Atlas will be passing through the inner solar system at a distance roughly between Earth and Mars. Not particularly close by astronomical standards, but close enough that solar radiation becomes significant, and more importantly, close enough that the object's velocity reaches its maximum. This is where orbital mechanics gets really interesting, and why the timing of the trajectory change during these 8 days is generating so much attention. There's a principle in spaceflight called the Oberth effect, named after the German physicist Hermann Oberth, who described it in the 1920s. It states that a propulsive maneuver, any burn that changes velocity, is most efficient when performed at the highest velocity point in an orbit. The reason is pure physics. Kinetic energy scales with the square of velocity, so the same delta V applied at high speed produces more total energy change than the same delta V applied at low speed. For spacecraft traveling through the solar system, this means you execute your major maneuvers at perihelion, the point where gravitational acceleration has brought you to maximum velocity, because that's where every bit of thrust gives you the most benefit. If you were designing a mission to explore an alien star system, and you wanted to adjust your trajectory to get a closer look at the inhabited planet, you would wait until perihelion. You would time your maneuver to coincide with the moment of maximum velocity and minimum solar distance, because that's when the fuel cost is lowest, and the trajectory change is most effective. It's not just efficient, it's optimal. And that's exactly what happened with 3i Atlas. The trajectory deviation occurred during the approach to perihelion, during the 8 days when velocity was peaking, during the exact window when any propulsive maneuver would be most effective. The timing isn't just suspicious, it's textbook. Now let me address the obvious question. Could natural outgassing produce this effect? Yes, absolutely. Comets naturally become more active as they approach the Sun because solar heating sublimates surface ices, creating jets of gas and dust that can act like small rocket engines, and those jets would naturally be most powerful near perihelion when heating is most intense. So timing alone doesn't prove anything artificial. What's unusual is the combination of factors: the magnitude of the trajectory change exceeding typical cometary thrust, the relatively modest coma suggesting limited outgassing activity, and the precision of the timing coinciding with the observational blackout. Any one of these factors is explainable. All of them together create a pattern that's harder to dismiss. There's another detail that's worth considering. At 1.36 astronomical units from the Sun, the solar energy flux is approximately 680 watts per square meter. That's the amount of sunlight hitting every square meter of the object's surface. For a nucleus estimated at 8 to 12 kilometers in diameter, the total cross-sectional area facing the Sun would be somewhere around 50 to 110 square kilometers, which translates to a total solar energy input of roughly 35 to 75 gigawatts. That's an enormous amount of power equivalent to dozens of large power plants. If you were an interstellar probe equipped with any kind of solar thermal propulsion system, something that uses sunlight to heat a propellant and create thrust, perihelion at 1.36 astronomical units would be the ideal moment to operate. You'd have maximum available power, maximum velocity for the Oberth effect, and you'd be hidden from Earth's view. The tactical advantages stack up in a way that's difficult to ignore. But what could we actually see during those 8 days? Very little, it turns out. The Solar and Heliospheric Observatory, SOHO, operates a coronagraph called LASCO that can image the region around the Sun by blocking out the solar disk with an occulting mask. But LASCO's field of view typically extends from about 1.5 to 30 solar radii, which translates to roughly 0.007 to 0.14 astronomical units from the Sun's centre. At 1.36 astronomical units, 3i Atlas was well beyond LASCO's observable range. The spacecraft wasn't designed to image objects at that distance during solar conjunction. Similarly, the Parker Solar Probe, which has been making close passes of the Sun since 2018, was not in a position to observe 3i Atlas during perihelion. Its orbital geometry placed it on the opposite side of the Sun during late October. What about Mars? Several operational spacecraft orbit Mars, including ESA's Mars Express and Trace Gas Orbiter, NASA's Mars Reconnaissance Orbiter, and MAVEN, and others. Could any of them have had a viewing angle on 3i Atlas during the solar conjunction period? The geometry is challenging. On October 25th, Mars was at approximately 1.64 astronomical units from the Sun, positioned at a solar elongation that placed 3i Atlas within roughly 30 degrees of the Sun as viewed from Mars' orbit. That's better than Earth's view, but still within the glare zone that makes optical observations extremely difficult. Additionally, the Mars orbiters are primarily designed for planetary observation, not deep space object tracking. Their instruments are optimized for surface mapping and atmospheric analysis, not for detecting and tracking faint cometary nuclei against the scattered sunlight background. Could they have captured something? Possibly, but there's been no indication that any Mars mission was tasked with observing 3i Atlas during this period. And even if they were, the data processing and public release timelines for these missions typically run weeks to months behind real-time operations, so we're left with a gap. 8 days when the object was moving through the most dynamically significant part of its trajectory, at the moment of maximum velocity and maximum solar energy availability, during a period when Earth-based observation was impossible and no known spacecraft had clear line of sight. That gap doesn't prove anything happened, but it creates space for possibility. And in that space, questions multiply. If the trajectory change was deliberate, whoever or whatever executed it chose the perfect window. If it was natural, the timing is an extraordinary coincidence. Either way, the fact remains that we cannot directly observe what happened during those 8 days. We can only infer from the before and after data, comparing the trajectory predicted before conjunction with the trajectory observed after emergence. And according to the amateur tracking networks and the revised JPL Horizons elements, those two trajectories don't match. Something changed, and it changed when we weren't watching. The emergence from solar conjunction is scheduled for October 29th, just 5 days from now as I'm recording this. That's when 3i Atlas will become visible again, when telescopes around the world will be able to reacquire the object and measure its position, velocity, brightness, and spectroscopic properties. Those observations will be critical. They'll either confirm that the trajectory deviation is real and sustained, or reveal that it was a measurement artifact that resolves once we have clear line of sight again. But until then, we're in the dark, literally and figuratively, trying to reconstruct what happened during a period when observation was impossible. And that uncertainty, that gap in knowledge, it's precisely what keeps this story compelling, because the next question we need to answer is not just what happened during those 8 days, but what physical mechanism could produce the velocity signature that observers are claiming to detect. When astronomers talk about trajectory, they're really talking about velocity. Position tells you where something is. Velocity tells you where it's going, and for an object like 3i Atlas, moving through the solar system at hyperbolic speed, velocity is everything. It's measured in three-dimensional space using coordinate systems that account for the Sun's gravity, the object's incoming direction, and the complex interactions with planetary masses. The specific measurements involve heliocentric velocity, which is speed and direction relative to the Sun as the central reference point, and barycentric velocity, which uses the solar system's center of mass as the reference. For interstellar objects, we typically use heliocentric coordinates because they're more intuitive and directly comparable to how we track comets and asteroids. Before the October 21st observations, JPL Horizons listed 3I Atlas, with a heliocentric velocity of approximately 67.8 km per second at its position on October 15th. That's extraordinarily fast, more than twice the escape velocity from the solar system at that distance. It's the speed of an object that's not bound to the Sun, that came from interstellar space and will return to interstellar space after this brief encounter. But velocity isn't just a single number, it's a vector, meaning it has both magnitude and direction, and the direction is described using components: radial velocity, which is the speed toward or away from the Sun, and tangential velocity, which is the speed perpendicular to the radial direction, essentially the sideways motion relative to the line connecting the object to the Sun. When the trajectory deviation was first reported, the claims centered on changes to the tangential component. This is significant because outgassing jets, the natural mechanism that can alter comet trajectories, typically produce forces that are radial or semi-radial, directed outward from the nuclear surface which is heated by the Sun. Pure tangential thrust perpendicular to the sunward direction would require jets that are asymmetrically distributed and precisely oriented, which is possible but less common. The observers who flagged the deviation noted that the velocity vector had rotated slightly, changing direction by what they calculated as 0.003 to 0.005 degrees over the course of several days approaching conjunction. That angular rotation, sustained over time, produces the positional offsets that grew from 1 million kilometers to 1.8 million kilometers by October 23rd. To quantify this, let's work through the math. If we assume the trajectory change required a delta V of 0, 15 kilometers per second, which is a conservative estimate based on the reported deviations, and we assume this velocity change was applied gradually over a period of 8 days, roughly 700,000 seconds, then the average acceleration would be 0.15 divided by 700,000, which gives us approximately 2 times 10 to the negative 7th meters per second squared. That's 0.000002 meters per second squared. For comparison, Earth's surface gravity is 9.8 meters per second squared, so we're talking about an acceleration roughly 50 million times weaker than what you feel standing on the ground. It's tiny, but sustained over days at the enormous mass of a cometary nucleus, it requires substantial force. Force equals mass times acceleration. If the nucleus mass is 400 billion kilograms, a mid-range estimate, then the required force is 400 billion times 0.000002, which equals 80,000 newtons. That's roughly the thrust of a single modern rocket engine, not a massive one, but not insignificant either. And that thrust has to be sustained continuously for 8 days. In terms of propulsion systems, what could produce this? A chemical rocket would require carrying propellant mass comparable to or exceeding the payload mass, which seems implausible for a natural object. An ion drive, the kind used on spacecraft like Dawn or Hayabusa, produces very low thrust, typically millinewtons to newtons, far below the 80,000 newtons needed. But scaled up, with sufficient power supply, an ion thruster could theoretically do it. Solar sails are another option, using radiation pressure from sunlight to generate thrust. At 1.36 astronomical units, solar radiation pressure on a perfectly reflective sail produces about 9 micronewtons per square meter. To get 80,000 newtons, you'd need a sail area of roughly 9 billion square meters, or a square sail about 95 kilometers on each side. That's enormous, probably detectable, and we haven't seen anything like that in the imaging attempts. The most plausible natural mechanism remains outgassing, but with the caveats I mentioned earlier. For cometary jets to produce 80,000 newtons of thrust, you'd need to be expelling roughly 8 kilograms of material per second at a velocity of 10 kilometers per second, or 80 kilograms per second at 1 kilometer per second. The actual velocity of cometary outgassing is typically around 0.5 to 1 kilometer per second, so you'd need mass loss rates of 80 to 160 kilograms per second. Over 8 days, that's 55 to 110 million kilograms of material expelled. For a comet with total mass around 400 billion kilograms, losing 100 million kilograms is only 0.25% of its mass completely feasible. But expelling that much material should produce a very bright, very extensive coma and tail, much more prominent than what's been observed. That's the disconnect. The effect requires substantial outgassing, but the visible evidence of that outgassing is modest. Now let's talk about Oumuamua, because the comparison is inevitable. In 2017, when that first confirmed interstellar object passed through our solar system, astronomers noticed it was accelerating slightly as it moved away from the Sun. The acceleration was small, about 5 times 10 to the -8 meters per second squared, even tinier than what we're discussing with 3i Atlas. After extensive analysis, the consensus explanation was outgassing, probably of hydrogen or some highly volatile substance that didn't produce visible coma. The acceleration profile matched what you'd expect from a comet being heated by the Sun, and even though we couldn't directly detect the outgassing, the physics worked. But the debate lingered because Oumuamua's shape, inferred from its brightness variations, appeared highly elongated, either cigar-shaped or pancake-shaped, very unusual for a natural object. That unusual geometry, combined with the unexplained acceleration, kept alternative hypotheses alive, including the suggestion by Avi Loeb that it could be a light sail or some kind of artificial probe. What makes 3i Atlas potentially more significant than Oumuamua is the magnitude and timing. The acceleration, if real, is stronger. The trajectory change occurred at perihelion, the dynamically optimal moment, and the observation suggesting deviation occurred during a period when the object was unobservable, which adds a layer of mystery that Oumuamua didn't have. Oumuamua's acceleration was detected and measured continuously as it left the solar system. With 3i Atlas, we have a before and after comparison across an 8-day blackout. That makes verification harder, but also makes the implications more dramatic if the deviation holds up under scrutiny. I want to emphasize again that these velocity measurements and trajectory deviations are being reported primarily by independent observer networks, not yet confirmed by official institutional announcements. The scientific process is slow, data needs to be verified, alternative explanations explored, peer review conducted. What we're seeing right now is the early stage of that process, playing out in semi-public through astronomy forums, preprint servers, and social media discussions. The formal papers will take months, but the fact that JPL updated the horizon's orbital elements suggests they've incorporated new data that changes the predicted path, which lends credibility to the claim that something is different about this object's trajectory. The velocity signature, if it's real, tells us that 3i Atlas is not following a simple gravitational path. It's being perturbed by some force, either internal outgassing or something else. And the characteristics of that perturbation, the magnitude, the direction, the timing, they're all consistent with what you'd engineer if you wanted to adjust a trajectory efficiently during a solar system flyby. That consistency doesn't prove intent. Natural processes can mimic optimized engineering. That's one of the beautiful coincidences of physics. But it does raise the question, and it's a question that's increasingly difficult to dismiss. What exactly happened to 3i Atlas during those 8 days of darkness? And are we looking at the velocity signature of an interstellar comet, or something that's making decisions about where it wants to go? That question hinges not just on velocity, but on what the object actually did physically at perihelion, and whether the changes we're seeing in its motion correspond to changes in its brightness, structure, and composition. Perihelion isn't just about position, it's about transformation. When a comet approaches the Sun, heat penetrates the surface, sublimating ices that have been frozen for billions of years. The nucleus begins to breathe, exhaling jets of gas and dust that create the coma and tail we associate with cometary activity. Brightness increases dramatically because the coma scatters sunlight across a much larger effective area than the solid nucleus alone. And if you're observing with spectroscopy, you start detecting specific molecular emissions, signatures of water, carbon monoxide, carbon dioxide, ammonia, methane, all the volatile compounds that make up cometary composition. Perihelion is when a comet becomes most itself, when the dormant ice ball transforms into an active dynamic system that reveals its true nature. For 3i Atlas, perihelion was predicted to occur on October 29, 2025, at a solar distance of 1.36 astronomical units. That's not particularly close, certainly nothing like sun-grazing comets that pass within a few solar radii and experience extreme heating. At 1.36 AU, solar flux is only about 50% of what Earth receives, so we wouldn't expect dramatic explosive outgassing, but we would expect measurable brightening, an expanding coma, and ideally, detailed spectroscopic measurements that could confirm the object's composition and activity level. The problem is that October 29th falls right at the end of the 8-day solar conjunction blackout, meaning the object becomes observable again just as it reaches perihelion. We don't have good data for the days leading up to it, the approach phase when activity would be ramping up. We're essentially blind until the moment of maximum solar proximity, and then we're trying to observe an object that's still within significant solar glare. But here's where things get interesting, and where some of the claims circulating among astronomy communities start to diverge from what you'd expect. According to preliminary magnitude estimates from observers who attempted to track 3I Atlas in early October before conjunction, the object's brightness was approximately magnitude 17 to 18, relatively faint, requiring mid-sized telescopes to detect. As it approached perihelion, the brightness should have increased significantly, potentially reaching magnitude 12 to 14 or even brighter, depending on how active the outgassing became. Brighter magnitude means more light, which usually correlates with more coma activity. But the reports emerging from late October observations, the ones trying to reacquire the object as it emerges from conjunction, they're suggesting that the brightness hasn't increased as much as expected. Some are claiming the object is actually dimmer than it should be at perihelion, remaining around magnitude 16 to 17, which would be very unusual. Now, before we spiral into speculation, let me clarify. These are preliminary, unverified reports from amateur networks attempting extremely difficult observations of an object still within 30 degrees of the Sun, fighting atmospheric scatter and twilight conditions. Official brightness measurements from major observatories won't be available for several more days, until November 3rd or later, when the object is far enough from solar glare to allow clean photometry. So the magnitude claims are uncertain, possibly affected by observational bias, equipment limitations, or atmospheric conditions. But if they're accurate, if 3I Atlas is genuinely dimmer at perihelion than predicted, that would be profoundly strange. It would suggest either that the object is less active than expected, producing less coma and therefore scattering less light, or that something about its surface or structure is suppressing outgassing. There's a hypothesis circulating, again unverified and speculative, that the nucleus might be rotating in a way that presents a less volatile surface toward the Sun during perihelion. Cometary nuclei are often irregularly shaped, lumpy objects with heterogeneous surfaces. Some areas are rich in ices, others are covered with dust and refractory material that doesn't sublimate easily. If the rotation axis and phase happen to position an ice-poor region toward the Sun during the approach to perihelion, outgassing would be suppressed, brightness would be lower, and thrust from jets would be reduced. It's plausible. But it would also be remarkably coincidental, and it doesn't easily explain the trajectory deviation that reportedly occurred during the same period. Reduced outgassing should correlate with reduced thrust, which should mean less trajectory perturbation, not more. Then there's the spectroscopic question. James Webb Space Telescope had 3I Atlas on its observing schedule for mid-October, attempting to capture high-resolution infrared spectra that could identify specific molecules in the coma and potentially even thermal signatures from the nuclear surface. The observations were conducted, but the data hasn't been publicly released yet. JWST operates on a proprietary period system, meaning the researchers who propose the observations have exclusive access to the data for a set period before it becomes available to the broader community. That's standard practice, designed to give observing teams time to analyse and publish their findings without being scooped. But it also means we're in the dark about what Webb might have detected. Did it see water, carbon monoxide, organic compounds, unusual volatiles? Or was the signal weaker than expected, consistent with the lower than predicted brightness? Hubble Space Telescope also targeted 3I Atlas in late September and early October, using its wide-field camera to capture visible light images of the nucleus and coma. Hubble's advantage is resolution. It can distinguish the central nucleus from the diffuse coma better than ground-based telescopes, allowing estimates of nucleus size and activity distribution. The images from those sessions showed a relatively compact coma, not the extensive fuzzy envelope you'd see from a highly active comet. The nucleus appeared to be intact, not fragmenting, and the coma brightness distribution suggested moderate jet activity, possibly from a few discrete venting regions rather than uniform surface outgassing. But again, these were observations from before perihelion, before the peak heating. The images captured during and after perihelion won't be available for several more weeks, limited by telescope scheduling and data downlink timelines. There's another detail that's generating attention, related to coma asymmetry. When cometary jets are active, they don't spray uniformly in all directions. They tend to be localized to specific surface features, sunlit areas where ices are exposed, and they create asymmetric coma structures. The shape and direction of the coma asymmetry can tell you where the jets are located on the nucleus and which way they're pointing. Some observers analyzing the limited pre-perihelion images of 3I Atlas have noted that the coma appears slightly elongated toward the sun-facing side, which is unusual. Normally, radiation pressure and solar wind push cometary material away from the sun, creating a tail that extends anti-sunward. An elongated coma directed toward the sun would suggest jets firing in a retrograde direction, opposite to the expected orientation. It's not impossible. Nucleus rotation could create sun-facing jets depending on the spin state and surface topography, but it's another oddity that doesn't fit the standard model. And then there's rotation. Cometary nuclei typically rotate with periods ranging from a few hours to a few days, and that rotation creates periodic brightness variations as different surface areas with different albedos rotate into view. Light curve analysis, measuring brightness over time, can reveal the rotation period and even constrain the shape of the nucleus. Some preliminary light curves from early October suggested a rotation period around 8 to 12 hours, but the amplitude of the brightness variations was small, indicating either a nearly spherical nucleus or a rotation axis aligned close to our line of sight. The problem is that small amplitude light curves make it difficult to track rotation state changes, and if the nucleus has changed its spin rate or orientation due to outgassing torques, we might not detect it clearly until we have better coverage. Why does rotation matter? Because outgassing jets create torques that can spin up or spin down the nucleus, and they can also change the orientation of the spin axis. This is called rotational dynamics, and it's been studied extensively with comets like 67P, which the Rosetta mission observed in extraordinary detail. If 3I Atlas underwent a spin state change during perihelion, that could affect which surface areas are heated, which jets are active, and potentially how the thrust vector from outgassing is directed. A change in rotation could even explain a trajectory perturbation if the thrust direction shifted. But tracking rotation requires continuous observation, which we didn't have during the conjunction blackout. We're trying to infer what happened from snapshots before and after, and that's extraordinarily difficult. Now let me address what might be the most controversial claim circulating right now, one that I want to frame very carefully because it's based on incomplete data and considerable speculation. There are reports, again from independent observer networks, that the nucleus of 3I Atlas might be smaller than initially estimated, potentially much smaller. The original size estimates, 8 to 12 kilometers in diameter, were based on brightness and assumed albedo, the reflectivity of the surface. If the surface is darker than assumed, reflecting less sunlight, then the object would need to be larger to produce the observed brightness. If the surface is brighter, more reflective, then the object could be smaller. Some observers are now suggesting, based on very preliminary analysis of brightness and coma extent, that the nucleus might be only 3 to 5 kilometers in diameter, significantly smaller than the initial estimates. Why would that matter? Because if the mass is smaller, then the thrust required to produce the observed trajectory deviation is also smaller. A 3-kilometer nucleus has roughly 1/8 the volume, and therefore 1/8 the mass of a 6-kilometer nucleus, assuming similar density. Less mass means less force needed to accelerate it, which makes the outgassing explanation more plausible. But it also deepens another mystery. If the nucleus is smaller, why is the coma so modest? Smaller nuclei typically have higher surface area to volume ratios, which means they heat up faster and outgas more vigorously per unit mass. A small nucleus should be very active at perihelion, producing a bright, extensive coma, but that's not what we're seeing, or at least not what the preliminary observations suggest we're seeing. The contradictions stack up. Trajectory change requires thrust. Thrust requires outgassing. Outgassing requires heat and volatiles. Heat is available at perihelion. But the brightness is low, the coma is modest, and the spectroscopic data is not yet public. So where does that leave us? On October 24th, 2025, 3 days after the trajectory deviation was first reported, and 5 days before official perihelion observations become available, we're in a state of profound uncertainty. The object did something during the 8 days of solar conjunction, something that changed its trajectory in a way that exceeded predictions. but we don't have clear physical evidence of what mechanism produced that change. The brightness is ambiguous, possibly lower than expected. The coma structure is unusual, possibly asymmetric in unexpected directions. The rotation state is uncertain. The size is uncertain. The composition, which could explain everything, is locked up in unpublished spectroscopy data that won't be available for weeks or months. We're assembling a puzzle with pieces that don't quite fit, and the picture that's emerging is either a comet behaving very strangely or something else entirely that we're trying to force into a cometary framework because that's the category we expect it to belong to. And the question that keeps nagging at researchers, the one that nobody wants to say out loud but everyone is thinking, is whether the strangeness at perihelion is just natural variability, or whether we witnessed something intentional happen during the only window when we couldn't watch. Distance is safety. In astronomy, when we talk about objects passing through the solar system, the primary question is always, how close? Because close means risk, even if that risk is infinitesimally small. It means potential gravitational interactions, possible collision trajectories, and most importantly for an object like 3I Atlas, it means we can study it better. Close objects are brighter, easier to image, easier to resolve spatially, and easier to track with radar if they come within a few million kilometers. So when observers started reporting that the trajectory deviation had reduced the projected Earth closest approach distance by 18 million kilometers, that wasn't just a number. It was a shift in what this object means for us, both scientifically and psychologically. Let's establish the baseline. The original trajectory prediction from JPL Horizons, based on observations from August through mid-October, indicated that 3I Atlas would make its closest approach to Earth in mid-December 2025 at a distance of approximately 280 million kilometers, roughly 87 astronomical units. That's farther than the Sun, substantially farther than Mars at its closest, nowhere near any kind of threat. At that distance, the object would remain a faint dot even in large telescopes, magnitude 14 to 16, requiring significant exposure time to capture useful data. But the revised trajectory, incorporating the observations from late October that show the deviation, now predicts a closest approach of approximately 262 million kilometers, roughly 1.75 astronomical units. The difference is 18 million kilometers, which sounds enormous, and it is on human scales, but in astronomical terms it's less than a 7% change in distance. Still, that 7% matters. Brightness falls off with the square of distance, so an object at 1.75 astronomical units is about 13% brighter than the same object at 1.87 astronomical units, all else being equal. That's the difference between a magnitude 15.5 object and a magnitude 15. Two objects, not dramatic, but enough to improve signal-to-noise ratio in spectroscopy and imaging. More importantly, the trajectory revision changes the geometry of how the object passes through the solar system. The original path had 3I Atlas approaching from the galactic plane direction, passing above Earth's orbital plane by about 15 degrees, executing a relatively simple hyperbolic swing around the Sun, and then departing toward the southern celestial hemisphere. The new trajectory, if the deviation is sustained, introduces an asymmetry. The object is no longer following a smooth, symmetric hyperbola. It's got a kink, a perturbation that alters the outbound path compared to the inbound path. That asymmetry is what's triggering conversations within planetary defense communities, not because there's any collision risk, there isn't, but because asymmetric trajectories are what you'd see if an object were being actively maneuvered. Natural objects follow conic sections, ellipses, parabolas, hyperbolas, curves defined purely by gravitational attraction to the Sun. When you add thrust, when you apply force that's not gravitational, you break the conic section. The path becomes irregular, and that irregularity is a signature of propulsion. Again, cometary outgassing is propulsion, it's just natural propulsion, so the asymmetry doesn't automatically imply anything artificial. But the fact that planetary defense networks are paying closer attention, running more detailed impact probability calculations, and extending observation campaigns, that tells you the professional community is taking the trajectory deviation seriously. The International Asteroid Warning Network, IAWN, is coordinating a monitoring campaign for 3I Atlas, running from November 27th through January 27th, 2026. IAWN is a collaboration organised under the United Nations Committee on the Peaceful Uses of Outer Space, designed to coordinate global efforts to detect, track, and characterize potentially hazardous near-Earth objects. Their involvement with 3i Atlas is not because the object is hazardous in the collision sense, but because it represents an unusual trajectory case that warrants detailed study, and because the monitoring campaign serves as a test of international coordination for tracking fast-moving objects. The campaign involves observatories across multiple continents, ensuring continuous coverage as Earth rotates, and it's designed to produce high-cadence astrometry, precise position measurements over time that can definitively constrain the trajectory and detect any ongoing perturbations. What they're looking for is whether the trajectory deviation observed in late October was a one-time event or an ongoing process. If the object has settled onto a new, stable hyperbolic path and is now following that path predictably, then whatever caused the deviation, outgassing or otherwise, has stopped or reached equilibrium. But if the position continues to deviate from predictions, if the trajectory keeps changing as the object moves away from the Sun through November and December, then we're witnessing sustained thrust, and that would be profoundly unusual. Cometary activity typically peaks near perihelion and declines as the object moves away from the Sun and surface temperatures drop. Sustained thrust beyond perihelion, maintaining or increasing in strength, would not fit the standard cometary model. It would require an internal energy source or a mechanism that's not dependent on solar heating, and that's the scenario that would truly elevate this from unusual to extraordinary. There's another trajectory milestone worth noting. In March 2026, 3i Atlas will make a distant pass by Jupiter, coming within approximately 0.8 astronomical units of the gas giant, nowhere near close enough for a significant gravitational interaction, but close enough that Jupiter's immense mass will slightly perturb the object's trajectory. Normally, that perturbation is predictable, calculable to high precision using n-body gravitational simulations. But if 3i Atlas is still undergoing non-gravitational acceleration in December and January, then the pre-Jupiter trajectory will be uncertain, which means the post-Jupiter trajectory will be even more uncertain. That uncertainty is what planetary defense specialists are trying to reduce. Because even though this object poses no threat, the tracking and prediction methodologies being developed and tested with 3i Atlas will be directly applicable to future objects that might pose real risks. It's a learning opportunity, and one that the global astronomy community is taking seriously. Now let's talk about something that's generating significant speculation, but needs to be addressed with extreme caution. The possibility that 3i Atlas could deploy something. If, and this is an enormous if based on zero evidence, if the object were not a natural comet but some kind of probe or carrier, the trajectory revision bringing it closer to Earth could be explained as intentional targeting for a secondary deployment. Drop a probe, release a sensor package, deploy a communication relay, whatever the hypothetical function might be, bringing the carrier vehicle closer to the target planet would reduce the deployment delta-V requirements and increase mission flexibility. This is pure speculation, the kind of scenario that gets discussed in SETI workshops and science fiction conferences, but it's worth understanding the logic because it's driving some of the more enthusiastic interpretations circulating online. The reasoning goes like this. An interstellar mission to our solar system would probably not involve landing a massive mothership on Earth or even entering a close orbit. The fuel costs are prohibitive, and the gravitational well of a planet is difficult to escape from. Instead, you'd do a fast flyby, retaining your hyperbolic excess velocity, and you'd deploy smaller probes that could decelerate independently, entering orbit or descending to the surface. The mothership continues onward, possibly visiting other planets in the system, possibly exiting to visit other stars, while the deployed elements remain behind to conduct their missions. If you were designing such a system, you'd want your closest approach to the target planet to occur after perihelion, after you've used the Oberth effect to adjust your trajectory, maximizing velocity and minimizing fuel expenditure. And that's exactly the geometry we're seeing with the revised 3i Atlas trajectory. Perihelion on October 29th, followed by Earth closest approach in mid-December, with the path adjustment occurring at perihelion bringing the approach 18 million kilometers closer. Again, let me be absolutely clear. There is zero observational evidence of any deployment, no secondary objects detected separating from 3i Atlas, no anomalous signals, no debris field, nothing. This is a thought experiment, not a detection. But it's a thought experiment that explains the observations within an engineering framework, and that's why it persists in discussions. If you assume technology, if you assume intent, The pattern fits. The problem is that assuming technology and intent is an extraordinary claim that requires extraordinary evidence, and we don't have that evidence. What we have is a trajectory that changed at a convenient time, by a convenient amount, in a convenient direction, and a collection of unusual but not impossible physical characteristics. That's not sufficient to conclude anything beyond natural processes, but it's sufficient to keep the question open and to motivate continued detailed observation. The proximity question ultimately is about two things: risk and opportunity. The risk is minimal. 262 million kilometers is an enormous distance, but it's being monitored anyway because unusual trajectories warrant attention. The opportunity is substantial because a closer approach means better data, better imaging, better spectroscopy, better chances to understand what this object actually is. And that's what the next several months are about. November observations to confirm the trajectory, December observations to refine closest approach parameters, January observations to measure post-encounter velocity and assess whether the object continues to deviate, and through it all, March 2026 Jupiter encounter, to see how the giant planet's gravity interacts with an object that might or might not be following purely gravitational dynamics. The proximity problem isn't about danger, it's about knowledge. We're close enough to learn something profound if we ask the right questions and interpret the answers honestly. But there's another piece of this puzzle that's been circulating since August, one that I've mentioned before but needs deeper examination because it connects composition to purpose, and it's possibly the most controversial claim associated with this entire story. Composition defines nature. When you want to know what something is, you study what it's made of. For comets, that means spectroscopy, analysing the light reflected or emitted from the object to identify specific molecules and atoms. Every element has a unique spectral fingerprint, absorption or emission lines at specific wavelengths that act like a barcode identifying its presence. Hydrogen, oxygen, carbon, nitrogen, iron, nickel, silicon. Each produces characteristic spectral features that astronomers can measure with extraordinary precision. For cometary science, the dominant signatures are usually water ice, sublimating into hydroxyl and hydrogen emission, carbon monoxide, carbon dioxide, ammonia, and various organic compounds. That's what comets are made of, primordial ices and dust left over from the solar system's formation. But in August 2025, a team using the Keck Observatory on Mauna Kea reported something different in the spectrum of 3I Atlas, something that didn't fit the standard cometary profile. The detection was nickel, specifically neutral nickel emission at 341, 5 nanometers, a line that appears when nickel atoms are being vaporized and excited by solar ultraviolet radiation. Nickel is not common in cometary spectra, but it's not unheard of either. Some comets show faint nickel and iron emission when they're very close to the Sun and surface temperatures are high enough to sublimate refractory metals, not just ices. What made the Keck detection unusual was the strength of the nickel signal relative to the expected iron signal. Iron and nickel are chemically similar, both are transition metals, and in natural solar system materials they almost always occur together because they were formed together in supernova nucleosynthesis and planetary differentiation processes. The ratio of iron to nickel in most asteroids, meteorites, and cometary dust is fairly consistent, roughly 15:1 to 20:1, iron dominant, nickel as a minor component, but the Keck spectrum showed strong nickel emission and very weak or absent iron emission. The ratio was inverted or at least drastically altered from what natural compositions produce. The team published a preliminary note in August highlighting this anomaly, suggesting it warranted further investigation, but they were careful not to claim it was definitive or unexplained. Spectroscopy is complicated. Line strengths depend not just on elemental abundance, but also on temperature, excitation state, dust opacity, and observing geometry. It's possible to suppress iron emission relative to nickel under certain conditions, particularly if the iron is bound up in minerals that don't release atoms easily. While nickel is present in a more volatile form, it's unusual, but not impossible. Avi Loeb, the Harvard astrophysicist who has become a prominent voice in the search for technological signatures beyond Earth, seized on the nickel anomaly as potentially significant. In September, he published a commentary suggesting that a nickel-rich iron-poor composition would be consistent with industrial alloys, specifically stainless steel, or other corrosion-resistant materials designed for long-duration space exposure. His argument was that natural processes don't typically separate nickel from iron effectively, whereas metallurgical engineering can create alloys with customized compositions optimized for specific applications. If 3I Atlas were manufactured, if it were constructed rather than accreted, a nickel-based alloy would make sense as a structural material. It's strong, resistant to oxidation, and would survive interstellar transit without degrading. Loeb's commentary generated substantial media coverage and polarized reaction within the astronomy community. Some researchers appreciated the willingness to explore unconventional hypotheses, arguing that SETI requires considering technological explanations when natural explanations are incomplete. Others criticized the commentary as premature, noting that the Keck data was preliminary, that alternative explanations had not been ruled out, and that invoking artificial origins without definitive evidence risks sensationalizing science and misleading the public. The debate became heated, dividing along familiar lines between those who advocate for aggressive exploration of technosignature hypotheses and those who prioritize conservative interpretation anchored in established natural processes. The key question is whether post-perihelion spectroscopy will confirm or refute the nickel anomaly. At perihelion, solar heating is at maximum, and if there are refractory materials, metals, or unusual compounds in the nucleus, they're most likely to be vaporized and detectable then. The James Webb Space Telescope's infrared spectroscopy, conducted in October but not yet publicly released, should have the sensitivity to detect metallic emissions if they're present in significant quantities. Ground-based observatories, including Keck, VLT in Chile, and Gemini North in Hawaii, are also scheduled to observe 3I Atlas in late October and early November as it emerges from solar conjunction. If the nickel emission remains strong and iron remains weak or absent, that would substantially strengthen the case that something unusual is happening compositionally. If the ratio normalizes, showing iron and nickel in expected proportions, then the August detection might have been an artifact of observing geometry, dust scattering, or some transient surface effect. There's another angle to consider, one that's more speculative but worth understanding because it connects to broader questions about interstellar objects. Some metallic asteroids in our solar system, M-type asteroids, are thought to be fragments of the cores of differentiated planetsimals, small planetary bodies that melted internally early in solar system history, allowing heavy metals like iron and nickel to sink to the center, while lighter silicates floated to form a mantle. When these planetsimals were later shattered by collisions, fragments of the metal-rich cores became M-type asteroids. These objects have surfaces dominated by iron-nickel alloys, not ices, and they don't outgas like comets. They're essentially flying chunks of metal, and they're quite valuable, the reason asteroid mining concepts often target M-types. Could 3I Atlas be an interstellar M-type asteroid rather than a comet? It's an intriguing idea, but it has problems. First, M-type asteroids don't typically show cometary activity, no coma, no outgassing, because there are no volatiles to sublimate. But 3I Atlas has displayed at least modest coma activity in the imaging attempts from September and October. Second, the trajectory designation as a comet. The C in its provisional designation was assigned based on observed activity. If it were purely rocky or metallic, it would be designated as an asteroid. So there's an inconsistency that needs to be resolved. Is it a metal-rich asteroid that somehow has volatiles producing a coma? Or is it a comet with unusual metal content? Or is it something else that doesn't fit neatly into either category? There's a hypothesis, again circulating among online communities and not yet represented in formal literature, that 3I Atlas could be a hybrid object, a metallic core with an icy mantle, essentially a comet built around a metal asteroid. Such an object could display cometary activity from the sublimating ice, while also showing metallic spectral signatures from the core if the ice layer is thin or patchy, and the core is exposed in some areas. Natural formation of such hybrids is difficult to explain. You'd need a scenario where a metal-rich fragment is later coated with ices, perhaps in the outer regions of a protoplanetary disk where temperatures are low, but it's not impossible. Alternatively, if you were constructing an interstellar probe, you might design it with a protective ice shell to shield instruments and propulsion systems from interstellar dust impacts and radiation during the long transit. The ice would ablate naturally as the probe enters a star system and approaches the Sun, revealing the functional core underneath. I want to stress again that this is speculation layered on top of incomplete data. We don't have confirmed measurements showing a metallic core. We don't have imaging resolution high enough to detect surface heterogeneity that would indicate a composite structure. What we have is one anomalous spectral measurement from August, some unusual brightness behavior, a trajectory that deviates from pure gravitational prediction, and a lot of unanswered questions. The nickel alloy enigma is compelling because it offers a material explanation, a physical property that could be tested and confirmed for why this object is behaving unusually. If the composition is truly anomalous, if it's not just rare but unexplainable by natural processes, then we have a legitimate mystery that demands unconventional hypotheses. But if the composition turns out to be within the range of natural variability, if November spectroscopy shows normal cometary signatures, then the enigma dissolves and we're left looking for other explanations for the trajectory deviation. The spectroscopic data expected in the coming weeks is absolutely critical. It will either deepen the mystery or begin to resolve it. And that's the nature of science at the frontier. You don't know which way the evidence will point until you collect it and analyse it honestly. The nickel anomaly is a thread, and if you pull on it, you might unravel the entire fabric of conventional explanations, or you might find that it was just a loose thread, easily trimmed and forgotten. But there's another thread that's equally strange, one that has nothing to do with composition or trajectory, and everything to do with timing and the behaviour of institutions when something unusual is detected. It's the thread that asks, what happens to the information and who controls its release? Information is power. When astronomers detect something unusual, the normal process is straightforward. Observe, measure, analyse, publish. Papers are submitted to journals, peer review happens over weeks to months, findings are announced at conferences, data is archived in public databases, and the scientific community collectively refines understanding through replication and critique. It's a slow process, deliberately so, because accuracy matters more than speed. But in the age of instant communication, when amateur astronomers can access the same sky as professionals, and when data can be shared globally in seconds, the traditional gatekeeping function of academic publishing is being challenged. And with 3i Atlas, some observers are claiming that the information flow has been unusually restricted, that data which should be public is being withheld or delayed, and that coordination between institutions suggests something more than routine scientific caution. The claims started circulating in late October, shortly after the trajectory deviation was first reported. Amateur astronomers who had been tracking 3i Atlas using publicly available ephemeris data from JPL horizons noticed that the system was occasionally slow to update, or that certain orbital parameters were listed as unavailable for brief periods. Horizons is a web-based interface that provides positional predictions for solar system objects based on continuously updated trajectory calculations. It's used by professional and amateur astronomers worldwide, and it's generally reliable. But according to posts on astronomy forums and social media, there were periods on October 22nd and 23rd when Horizons either didn't return results for 3i Atlas or returned outdated predictions that didn't match fresh observational data. Now, before this gets framed as a conspiracy, let's clarify what's actually normal. Horizons updates are not instantaneous. When new observational data comes in, especially data that significantly changes the trajectory solution, the JPL team needs to recompute the orbital elements, validate the solution, ensure it converges correctly, and then push the update to the public database. That process can take hours or even a day or two if the data is complex or if there are computational issues. Additionally, if multiple observers are submitting conflicting data, the team might hold off on updating until they can assess which observations are reliable. So temporary delays or unavailability are not inherently suspicious. They're part of normal operations when dealing with a newly characterized object with an evolving trajectory solution. But what's fueling suspicion is the lack of transparency. JPL didn't issue a notice explaining that the trajectory was being updated, or that there were unusual observations requiring analysis. The update just happened, silently, and users who were refreshing the Horizons page noticed the ephemeris had changed without announcement. In a community already primed to look for anomalies, that silence reads as evasion, even if it's just standard procedure. The pattern is familiar from other controversial objects, particularly Oumuamua, where delays in data release and lack of official comment created information vacuums that speculation rushed to fill. There are also claims, more difficult to verify, that some observatories that obtained data on 3i Atlas during late October are not sharing their measurements publicly as quickly as usual. Normally, astrometric data, precise position measurements, are submitted to the Minor Planet Center, the IAU designated clearinghouse for solar system object observations, within days of observation. The data is then incorporated into orbit determinations and made available to the global community. But according to some amateur astronomers monitoring the MPC submission logs, there have been fewer submissions for 3i Atlas than expected, given the number of facilities known to be observing it. The suggestion is that some institutions are holding data pending further analysis or coordination, possibly because the results are surprising and they want to verify before releasing. Is there any truth to this? It's hard to say. Academic research timelines are genuinely slow. If a professional observatory captures data that shows something unusual, the natural instinct is to verify, to conduct additional observations, to consult with colleagues before making claims that could be embarrassing if wrong. And if multiple institutions are seeing similar anomalies, they might coordinate informally, sharing data privately before making it public, to ensure they're interpreting correctly and not all making the same systematic error. That's not suppression, that's due diligence. But from the outside, especially to observers who are not part of those internal communications, it looks like information is being controlled. Then there's the question of NASA's public communication. As of October 24th, NASA has not issued any press releases or official statements about 3i Atlas beyond the initial announcement in July, when the object was first classified as interstellar. There's been no comment on the trajectory deviation, no acknowledgement of the unusual spectroscopic findings, no updates on the JWST observations. Silence. Now, NASA communicates about solar system objects primarily through the Planetary Defense Coordination Office and the Center for Near-Earth Object Studies. These offices typically issue statements when there's public safety relevance, impact risk, or significant scientific milestones. For an object like 3i Atlas, which poses no threat and whose scientific significance is still being assessed, no comment is arguably appropriate. There's no obligation to provide running commentary on every unusual measurement, especially when those measurements are preliminary and under investigation. But the absence of official communication creates space for unofficial narratives to flourish. On Reddit, Twitter, YouTube, forums dedicated to UFOs and UAPs, the silence is being interpreted as confirmation that something is being hidden. The logic is circular. If it's not important, why aren't they saying anything? If it is important, why aren't they saying anything? Either way, silence equals suppression in the minds of those predisposed to distrust institutions, and that distrust, fair or not, is amplified by historical precedents where governments and scientific establishments did withhold information about aerial phenomena, military encounters with unidentified objects, and classified space surveillance data. I think it's important to distinguish between legitimate institutional caution and actual suppression. Caution means waiting for peer review, verifying data, avoiding premature claims that could mislead the public. Suppression means intentionally hiding information that the public has a right to know, preventing scientists from sharing findings or coordinating narratives to obscure truth. I have seen no credible evidence of suppression related to 3i Atlas. What I see is caution, possibly excessive caution, born from a scientific culture that penalizes public mistakes more harshly than private uncertainty. That caution frustrates people who want answers immediately, and it feeds distrust among those already inclined to believe that institutions lie. The tracking network isn't dark in the sense that observations have stopped. Dozens of telescopes are actively monitoring 3i Atlas, and data is being collected continuously. What's dark is the public interpretation of that data, the official narrative that contextualizes what the observations mean. And that darkness, that absence of authoritative voice, is where speculation thrives. Amateur astronomers are doing incredible work. Some of the initial detections of the trajectory deviation came from amateur networks, and their contributions are genuinely valuable. But without coordination, without expert analysis, without institutional validation, the signal gets lost in noise. Claims multiply, some accurate, some exaggerated, some completely mistaken, and the public has no reliable way to distinguish. So where does that leave us on the information question? We're in a gap between detection and understanding, between preliminary observations and confirmed conclusions. That gap is uncomfortable, especially for an object as intriguing as 3i Atlas, and the temptation to fill it with speculation is powerful. But gaps are temporary. November observations will bring clarity. The IAWN monitoring campaign starting late November will bring systematic coordinated data. JWST spectroscopy results will eventually be published. Peer-reviewed papers will emerge, probably by early 2026, synthesizing all the findings. The information will come. The question is whether we can tolerate the uncertainty in the meantime, or whether we'll construct narratives that satisfy our need for explanation, but diverge from what the evidence actually supports. And while we wait for information to flow, there's another question worth exploring, one that's purely hypothetical but intellectually rigorous. If this object were artificial, what would that actually mean from an engineering standpoint? Let's conduct a thought experiment. Not a conclusion, not a claim, but a structured exploration of what would be required if, purely hypothetically, 3i Atlas were not a natural object but an artificial one, a probe or spacecraft sent by a non-human intelligence to explore our solar system. What would the engineering look like? What design constraints would apply? What mission profile would make sense? This isn't about proving anything, it's about understanding what the hypothesis actually entails, because if we're going to seriously consider technological explanations, we need to be rigorous about what technology would be required and whether observed parameters are consistent with that requirement. First, propulsion. We've established that to produce the observed trajectory change, approximately 0.15 kilometers per second delta V, applied over 8 days, you need sustained thrust of roughly 80,000 newtons for a 400 billion kilogram mass. What propulsion system could deliver that? Chemical rockets are out. They require enormous propellant mass, typically 60% to 90% of total vehicle mass for delta V values, even a fraction of what we're discussing. An interstellar probe would not carry chemical propellant, because the mass penalty is absurd over interstellar distances. Ion drives are more efficient, using electric fields to accelerate ions to very high exhaust velocities, allowing much less propellant mass for the same delta V. But conventional ion drives produce very low thrust, millinewtons to tens of newtons, nowhere near 80,000 newtons. You'd need to scale up by factors of thousands, which implies enormous power supplies. Where would the power come from? Solar is the obvious answer when you're this close to a star. At 1.36 astronomical units, solar flux is about 680 watts per square meter. To generate 80,000 newtons with an ion drive, assuming specific impulse around 3,000 seconds, which is typical for xenon ion thrusters, the power requirement would be in the range of 100 to 200 megawatts. That's the output of a large terrestrial power plant. To collect 150 megawatts from sunlight at 36 AU, you'd need a solar panel area of roughly 220,000 square meters, which is a square collector about 470 meters on each side. That's enormous, easily detectable in imaging, and we haven't seen anything like that. So either the power generation is vastly more efficient than our technology, using some advanced photovoltaic or thermal conversion system, or the propulsion mechanism is something we don't use, something that doesn't require as much power. Solar thermal propulsion is an alternative. You use mirrors or lenses to concentrate sunlight onto a reaction chamber, heating a propellant, hydrogen would be ideal, to extremely high temperatures and then expelling it through a nozzle. The exhaust velocity can be very high, 8 to 10 kilometers per second, much better than chemical rockets, and you don't need to carry an energy source because the sun provides it. But you still need propellant mass, and for a delta V of 0.15 kilometers per second, with exhaust velocity around 8 kilometers per second, you'd need propellant mass roughly 2% of the vehicle mass, about 8 billion kilograms. That's a lot, but it's conceivable if the probe is mostly propellant tanks. The challenge is storage, keeping hydrogen or another propellant in cryogenic liquid form over interstellar transit timescales, potentially thousands of years. You'd need insulation, active cooling, systems to prevent boil-off. It's technically feasible, but complex. Another option, nuclear propulsion, either fission or fusion. A nuclear reactor provides power independent of sunlight, useful for the interstellar cruise phase and for maneuvering in any star system regardless of solar distance. Fission reactors are proven technology. We've built them for spacecraft, though nothing at the scale needed for 80,000 newtons thrust. Fusion is more speculative, but if achievable, It offers much higher energy density and cleaner operation. With fusion, you could heat propellant to extreme temperatures, or use the fusion products directly as exhaust. The thrust and efficiency would be excellent, but the engineering complexity is immense, and the mass of the reactor, shielding, and fuel become significant. Still, for an advanced civilization capable of interstellar travel, nuclear propulsion is probably the baseline assumption. Now let's think about mission architecture. Why would you send a probe to another star system? The most obvious reason: to gather information. You want to know if there are planets, whether any are habitable, whether any host life or technological civilizations. You might send the probe with instructions to observe, measure, and potentially report back. But communication over interstellar distances is extraordinarily difficult. Radio signals travel at light speed, so a message from a probe in our solar system to a home system 50 light-years away takes 50 years to arrive, and another 50 for a response. Real-time control is impossible. The probe has to be autonomous, making decisions based on pre-programmed instructions and onboard artificial intelligence. Given those constraints, what would a sensible mission profile look like? You'd probably use the star's gravity to brake and maneuver, executing a hyperbolic trajectory that lets you survey the system without requiring the massive fuel expenditure of orbital insertion. You'd time your maneuvers to maximize efficiency, using perihelion for the Oberth effect, just like we do with our spacecraft visiting the outer planets. You'd collect as much data as possible during the flyby, measuring planetary parameters, atmospheric compositions, electromagnetic emissions, anything that indicates habitability or technology. And if you found something interesting, a planet with biosignatures or artificial signals, you might adjust your trajectory to get a closer look, trading some of your hyperbolic excess velocity for a trajectory modification that improves observational geometry. That's exactly what the 3i Atlas trajectory deviation accomplishes. The revised path brings the object 18 million kilometers closer to Earth, improving observation conditions, increasing the duration of close approach, and potentially allowing for deployment of secondary instruments if the probe carried any. It's a minor course correction by interstellar mission standards, but it meaningfully improves mission return. If you were designing this mission, it's exactly what you'd do. And the fact that the correction happened during solar conjunction, when Earth-based observation was impossible, that could be operational security, minimizing the chance of detection during the maneuver, or it could simply be coincidence, the optimal time from a physics standpoint regardless of who's watching. But here's the critical question. If this were a probe, why no communication? We've been listening for radio signals from 3i Atlas since it was identified as interstellar, using facilities like the Breakthrough Listen project at the Green Bank Telescope and Parkes Observatory. No signals have been detected, nothing in the standard SETI frequency bands, no unusual modulation, no narrowband emissions that would indicate artificial origin. The silence is deafening. If the object were trying to communicate, or even if it were just leaking radio emissions from internal electronics, we should have detected something by now. The absence of signals is one of the strongest arguments against the technological hypothesis. Unless the probe is deliberately silent, operating in a stealth mode, or using communication methods we can't detect, quantum entanglement, gravitational waves, neutrino beams, exotic physics that we haven't discovered yet. There's also the question of stealth. If you're an advanced civilization exploring the galaxy, do you want to be detected? Maybe not. First contact could be risky, unpredictable, potentially dangerous. You might prefer to observe without revealing your presence, gathering data covertly, assessing whether the emerging civilization is hostile, cooperative, or irrelevant. In that case, you'd design your probe to look natural, to mimic the appearance and behavior of a comet or asteroid, blending into the background of solar system objects. You'd minimize electromagnetic emissions, avoid obvious geometric structures, use passive sensors, and execute maneuvers only when necessary and ideally when unobservable. The 3i Atlas profile, if interpreted through this lens, fits the stealth hypothesis almost perfectly. It looks like a comet, behaves mostly like a comet, but with subtle anomalies that could be explained either as unusual natural properties or as imperfect mimicry. Now, let me pump the brakes hard on this speculation, because it's incredibly easy to construct narratives that fit observations retroactively, especially when the observations are incomplete and ambiguous. This is a classic example of what's called the confirmation bias trap. If you start with the hypothesis that the object is artificial, You can find ways to interpret every anomaly as supporting that hypothesis. Trajectory deviation, propulsion, nickel emission, industrial alloy, modest coma, stealth coating, lack of signals, deliberate silence. Each piece of evidence gets filtered through the assumption, and the narrative becomes self-reinforcing. But that's not how science works. Science demands that you seriously consider alternative explanations, that you actively try to disprove your hypothesis rather than confirm it, and that you proportion your confidence to the strength of the evidence. So let's apply that standard. What natural explanations remain plausible? The trajectory deviation could be vigorous asymmetric outgassing from a rotating nucleus with localized volatile-rich regions. The nickel emission could be a real, but rare compositional anomaly, perhaps from an interstellar comet that formed in a chemically unusual environment around a different star. The modest coma could reflect low volatile content or a dust-mantled surface that suppresses sublimation. The timing during solar conjunction could be pure coincidence. Perihelion is when cometary activity peaks, so it's exactly when you'd expect trajectory perturbations from outgassing. The absence of radio signals is expected. Natural objects don't emit radio signals unless they are interacting with stellar magnetic fields in specific ways, which doesn't apply here. All of these natural explanations are plausible. None require invoking unknown physics or extraordinary engineering, and by Occam's razor, the principle that simpler explanations are generally preferable when they fit the evidence equally well, we should default to natural explanations until they are definitively ruled out. We're not there yet. The anomalies are interesting, worth investigating, but they're not conclusive, and that's the honest assessment. The engineering hypothesis is internally consistent. It could explain the observations, but it's not necessary to explain them. Natural processes can do the job, even if they require the object to be somewhat unusual. But here's why the engineering hypothesis won't go away, why it persists in discussions and will continue to, until we have definitive compositional and behavioral data. It's because we know, with absolute certainty, that technological civilizations exist in the universe. We are one. We've sent probes beyond our solar system, Voyager 1 and 2, Pioneer 10 and 11, New Horizons, all of them are now in interstellar space or will be soon. If another civilization around another star did the same thing, sending probes to explore neighboring star systems, some of those probes would eventually reach us. The galaxy is billions of years old. Civilizations could have risen millions or billions of years before us, and their probes could be everywhere, drifting through the cosmos, occasionally passing through star systems like ours. The question isn't whether interstellar probes could exist. The question is whether 3I Atlas is one. And to answer that, we need better data, which is exactly what November is going to provide, and why the anticipation is building to almost unbearable levels among those of us following this story. November 3rd, 2025. Mark that date because that's when the fog starts to lift, when 3I Atlas emerges fully from solar glare and becomes accessible again to telescopes worldwide. For 13 days, since October 21st when it entered solar conjunction, the object has been hidden, observable only intermittently and with great difficulty through the overwhelming brightness of the Sun. But on November 3rd, the angular separation from the Sun exceeds 35 degrees, placing the object in dark sky for the first time since mid-October. Ground-based observatories will reacquire it, measure its precise position, track its brightness, capture high-resolution spectra, and most importantly, determine whether the trajectory deviation reported in late October is real or an artifact of difficult observing conditions. The European Space Agency has prioritized 3I Atlas for observation using their ground-based assets and potentially the JUICE spacecraft, which is currently en route to Jupiter, but carries instruments capable of deep space observations if tasked. ESA's interest stems from both scientific curiosity and coordination with the International Asteroid Warning Network, IAWN, which will begin its formal monitoring campaign later in November. But the early November observations are critical for establishing the baseline. If 3I Atlas is where the revised JPL Horizons predictions say it should be, then the trajectory deviation is confirmed. If it's back on the original predicted path, then the deviation was a measurement error, and we can all relax and return to treating it as an interesting but ultimately normal interstellar comet. The Keck Observatory on Mauna Kea, the facility that detected the nickel emission anomaly back in August, has dedicated telescope time scheduled for November 5th and 7th, specifically targeting 3I Atlas with high-resolution spectroscopy. They'll be looking at the same wavelength region where nickel was detected, measuring whether the emission is still present, whether its strength has changed, and critically, whether iron emission has appeared or remained suppressed. If the nickel-to-iron ratio normalizes, showing expected proportions, then the August detection was likely a fluke, a transient surface effect or instrumental artifact. If the anomaly persists, if nickel remains dominant and iron remains weak, that's when the compositional questions become urgent and unavoidable. The Very Large Telescope in Chile, operated by ESO, has an observation window starting November 8th. VLT's advantage is its powerful spectroscopic instruments, particularly UVES and ESPR-ESSO, which can resolve extremely fine spectral details and detect faint emission lines that smaller telescopes might miss. The VLT observations are designed to search for organic molecules, complex hydrocarbons, and amino acid precursors, signatures that would indicate the object is rich in prebiotic chemistry. If 3I Atlas is a comet from another star system, it potentially formed in a different chemical environment, around a star with different metallicity or in a disk with different temperature and pressure history. Detecting unusual organic compounds would be scientifically thrilling, revealing how planet formation chemistry varies across the galaxy. Gemini North in Hawaii is scheduled for November 12th and 15th, focusing on visible and near-infrared imaging to track coma structure and nucleus rotation. The goal is to capture light curves, brightness measurements over time that reveal rotation period and possibly shape asymmetry. If the nucleus rotation state has changed since September, if it's spinning faster or slower or wobbling, that would indicate torques from outgassing, which would support the natural comet explanation. But if the rotation appears stable, unchanged despite perihelion heating, that would be odd, because active comets typically experience rotational changes due to asymmetric jet thrust. And then there's James Webb, which, as I mentioned earlier, observed 3I Atlas in October but hasn't released data yet. Webb operates on a proprietary period system, but for high-profile targets, especially those with time-sensitive implications, data can be released early if the observing team chooses. The Webb observations included mid-infrared spectroscopy using the NIRSPEC and MIRI instruments, capable of detecting thermal emission from the nucleus and identifying specific molecules in the coma. If Webb detected unusual thermal signatures, hotspots, or unexpected molecular species, that data could fundamentally reframe our understanding of the object. But we won't know until the team publishes or presents findings at a conference, and the next major astronomy conference is the American Astronomical Society meeting in January 2026. Hubble is also back in the game. After perihelion, when the object is farther from solar glare, Hubble's pointing restrictions relax, allowing it to target 3I Atlas again with its high-resolution imaging cameras. The goal is to look for structural changes, fragmentation, or asymmetry in the nucleus that might indicate stress from heating or internal activity. Cometary nuclei sometimes fracture near perihelion due to thermal expansion or internal pressure buildup from sublimating ices. If 3I Atlas has fragmented, producing multiple separate pieces, that would definitively prove it's a natural icy object. But if the nucleus remains intact, monolithic, showing no signs of stress or fragmentation despite perihelion heating, that raises questions about its internal structure and composition. There's another measurement that's absolutely critical, but often overlooked by non-specialists: astrometry, the precise measurement of position over time. Astrometry is how we refine orbital elements and detect trajectory perturbations. The IAWN campaign, starting November 27th and running through January 27th, is fundamentally an astrometry campaign. Dozens of observatories will measure 3I Atlas positions every few nights, creating a dense time series of data that can reveal even tiny accelerations. If the object continues to deviate from a purely gravitational trajectory, if its position consistently differs from predictions by growing amounts, then we're witnessing sustained non-gravitational acceleration. That would be the smoking gun, the evidence that something is actively propelling the object beyond what solar gravity and radiation pressure can account for. The decision tree for November observations looks like this. If position matches revised predictions and brightness is normal, and spectrum shows typical comet composition, then trajectory deviation was real, but explained by normal outgassing, case closed. If position matches revise predictions but brightness is anomalously low and spectrum shows unusual metal content, then we have a compositionally strange comet that requires new models. If position continues to deviate and brightness is variable and spectrum is ambiguous, then we're in uncharted territory, and the technological hypothesis moves from fringe speculation to legitimate scientific consideration. And if position matches original predictions, meaning no deviation at all, then the October reports were errors, and we return to treating 3i Atlas as interesting, but not extraordinary. How long until we know which branch of that decision tree we're on? For position data, November 3rd through 7th observations will be conclusive. Observers will have clear line of sight, multiple facilities will independently measure coordinates, and by November 10th we'll know definitively whether the trajectory changed. For spectroscopy, it depends on data processing timelines. Keck and VLT typically release preliminary results within days to weeks, especially for high-interest targets. So by mid to late November, we'll have compositional data that either confirms or refutes the nickel anomaly. For brightness and rotation, that requires sustained observation over weeks to build light curves and track variability. So December might be when those results solidify. And then there's the wild card, unexpected discoveries. Sometimes the most important findings are the ones you didn't anticipate. Maybe Webb detected something in infrared that nobody predicted, thermal asymmetry suggesting internal heat sources, or spectral features indicating molecules that shouldn't exist in cometary environments. Maybe Hubble imaging reveals surface structures, geometric patterns, or reflectivity variations that don't match natural terrain. Maybe radio observations, even though they've been negative so far, suddenly detect a transient signal, a brief burst that suggests the object activated something during perihelion. Science is full of surprises, and with an object as unusual as 3i Atlas, the probability of surprise is higher than usual. What I'm watching for personally, what I think will be the clearest indicator of whether this is truly extraordinary, is consistency. If multiple independent lines of evidence all point in the same direction, if the trajectory deviation is real, and the composition is anomalous, and the brightness behavior is unexplained, and the rotation state is unusual, then the convergence of anomalies becomes compelling. Any single anomaly can be dismissed as rare but natural variability. But when multiple anomalies align, when they all suggest something outside the standard model, that's when you have to seriously entertain alternatives. Conversely, if the anomalies dissolve under scrutiny, if trajectory resolves as normal outgassing and composition turns out typical, and brightness matches predictions, then 3i Atlas will join the long list of objects that seemed extraordinary briefly, but turned out to be ordinary upon closer examination. Either outcome is valuable. If it's ordinary, we've learned that interstellar comets behave basically like solar system comets, which tells us planet formation is fairly uniform across the galaxy. If it's extraordinary, we've potentially detected something that redefines our place in the universe, and that's the beauty of doing this in real time, watching the evidence accumulate, adjusting our understanding as new data arrives. We're not reading about this in a history book. We're living through it day by day, observation by observation, question by question. November is going to give us answers, but those answers will inevitably generate new questions, and that process, the iterative refinement of knowledge, that's what science is. And while we wait for the data to resolve the mystery of what 3i Atlas is, there's a larger question worth contemplating, one that transcends the specifics of this one object and asks what it would mean if the extraordinary explanation turned out to be correct. Let's think through what happens if 3i Atlas is confirmed as artificial, if the trajectory deviation is sustained and unexplained by natural processes, if the composition shows clear evidence of engineering, if somehow, against all default expectations, we conclude that this object is not a comet but a probe sent by a non-human intelligence. What would that actually mean? How would we respond? What changes for humanity? These aren't idle questions. They're scenarios that SETI researchers, astrobiologists and policy experts have been considering for decades, knowing that eventually, possibly in our lifetimes, we might face exactly this situation. And while the probability that 3i Atlas is that case remains low, the implications are so profound that exploring them is worth the time, because preparing for the extraordinary is how we avoid panicking when it arrives. The first institutional response would come from SETI protocols, specifically the protocols established by the International Academy of Astronautics SETI Committee. These are guidelines, not laws, but they represent the consensus among scientists about how to handle the detection of extraterrestrial intelligence. The protocols outline a verification process, independent confirmation by multiple facilities, ruling out terrestrial and natural explanations, peer review of findings, and only then public announcement. The goal is to avoid false alarms, the kind of premature claims that damage credibility and create public confusion. If a research team concluded that 3i Atlas showed technological signatures, they would follow these protocols, contacting other observatories, sharing data privately, conducting exhaustive checks before going public. Interestingly, on October 16th, 2025, just 5 days before the trajectory deviation was first reported, the IAAS-ETI committee released an updated version of their protocols, the first major revision since 2010. The timing is coincidental. The update had been in development for over a year, but it sparked speculation online that the revision was motivated by something specific, perhaps early observations of 3i Atlas, or another object that prompted rethinking how detection scenarios should be handled. The updated protocols emphasize transparency, international coordination, and the importance of communicating uncertainty honestly to the public. They also address scenarios beyond radio signals, including detection of technological artifacts, megastructures, or probes, recognizing that first contact might not come through intentional communication, but through discovery of physical objects. If SETI protocols were activated for 3i Atlas, what would happen next? First, a rapid convening of expert panels bringing together astronomers, physicists, engineers, and potentially anthropologists and psychologists to assess the evidence and plan response. NASA would likely coordinate US involvement, working with the National Science Foundation, the Department of Defense, and the White House Office of Science and Technology Policy. Internationally, coordination would happen through the United Nations Office for Outer Space Affairs, the same body that oversees IAWN and planetary defense. The goal would be to present a unified scientific assessment, avoiding the chaos of conflicting national narratives or premature military responses. Public communication would be extraordinarily delicate. The announcement would need to convey that something significant has been detected without triggering panic, that the object poses no threat, that we're gathering more information, and that the discovery, if confirmed, represents a scientific milestone, not a crisis. Historical precedents are not encouraging. When the WOW signal was detected in 1977, a strong narrowband radio signal from space that matched SETI predictions, it generated enormous public excitement and speculation, but because it was never detected again, it faded into ambiguous history, neither confirmed nor explained. With Oumuamua in 2017, the public reaction was mixed: interest from space enthusiasts, indifference from most, and persistent conspiracy theories from others. With 3i Atlas, if confirmed as artificial, the reaction would be orders of magnitude larger because it's not a distant radio blip or an object already leaving the solar system. It's here, right now, observable, potentially still maneuvering. Would there be panic? Probably not widespread, but localized anxiety is likely, especially among communities predisposed to fear of the unknown or distrust of official narratives. Religious communities would grapple with theological implications, debating what non-human intelligence means for concepts of creation, divinity, and humanity's unique role. Philosophers and ethicists would explore questions of contact protocols, whether we should attempt communication, whether silence is safer. Military and national security establishments would assess whether the object represents any surveillance or strategic threat, whether it's collecting data about Earth's technology, resources, or vulnerabilities. And scientists would be racing to gather every possible measurement before the object leaves the inner solar system and becomes unobservable. There's also the question of what we'd try to do. Could we send a spacecraft to intercept 3i Atlas? The trajectory is hyperbolic, moving fast, and it will exit the inner solar system by early 2026, beyond the orbit of Mars and continuing outward. Catching it would require a mission launch with extraordinary delta-V, more than any existing rocket can deliver without years of gravitational assists. We couldn't do it quickly. A realistic mission would take years to plan and decades to execute, by which time the object would be far beyond reach. So we'd be limited to remote observation, watching it depart, hoping it does something else that reveals more about its nature and origin. That helplessness, the inability to interact directly, would be frustrating for many, but it's the reality of interstellar distances and the physics of propulsion. Now let's consider the implications if the object is real and remains silent, never attempting communication, simply observing and then leaving. What would that tell us? It would suggest that whoever sent it prioritizes observation over contact, that they're studying us without interfering, adhering to some form of non-interference principle, a prime directive as science fiction has popularized. It would confirm that we're not alone, that intelligence exists elsewhere, but it would also confirm that they're not interested in or capable of immediate interaction. That realization would be both comforting and isolating. Comforting because it means they're not hostile, at least not overtly, not attempting conquest or exploitation. Isolating because it means we remain alone in practical terms, unable to communicate, unable to learn from them, unable to join whatever community of intelligences might exist in the galaxy. On the other hand, if the object attempts communication, if it transmits a signal after perihelion, or deploys a device that begins broadcasting, then we're in entirely different territory. We'd have to decide how to respond, whether to answer, what to say, who speaks for Earth. The SETI protocols recommend that any response should be coordinated internationally, that no single nation or institution should unilaterally represent humanity. But the reality is that coordination is slow, and if a response opportunity is time-sensitive, decisions might be made quickly by whoever has the capability. That prospect worries many researchers, because first impressions matter, and a poorly considered response could have consequences we can't predict. There's a deeper implication too, one that's more philosophical than practical. If 3i Atlas is artificial, it means that interstellar travel, or at least interstellar probe missions, are feasible. It means that the vast distances between stars are not insurmountable barriers, that civilizations can send emissaries across light years and expect them to arrive functional. That would profoundly change our understanding of what's possible, what timelines govern galactic exploration, and what our own future might look like. If they can send probes here, we can send probes there, eventually, given enough time and technological advancement. It reframes space exploration from a distant dream to an achievable goal, one that requires patience and commitment, but not miraculous breakthroughs. And finally, there's the societal impact. Confirmation of extraterrestrial technology would be the most significant event in human history, more transformative than any scientific discovery to date, because it would fundamentally alter our self-conception. We'd no longer be the only known intelligence, the sole experiment in consciousness and civilization. We'd be one among potentially many, our planet one node in a network of inhabited worlds. That realization could inspire unity, a recognition that our differences as nations and cultures are trivial compared to the gulf between us and them, a perspective shift that might drive cooperation on global challenges, or it could deepen divisions as different groups interpret the discovery through their own ideological lenses, creating conflict over how to respond or what it means. But here's what I want to emphasize as we close this section and this script. We are not there yet. Nothing has been confirmed. The anomalies are real, the questions are legitimate, the investigations are ongoing, but the extraordinary explanation, the technological hypothesis, remains speculative, unsupported by definitive evidence. And that's where we need to hold the line, resisting the temptation to leap to conclusions that satisfy our curiosity, but outpace the data. Science demands patience, rigor, and humility. It demands that we follow the evidence wherever it leads, but that we don't run ahead of it, constructing castles of inference on foundations of possibility. November will bring clarity, or at least more data. December will bring additional observations as 3i Atlas reaches closest approach to Earth. January will bring the synthesis of findings from the IAWN campaign. And by mid-2026, peer-reviewed papers will emerge, representing the formal scientific consensus on what this object is and what it means. Until then, we watch, we wait, we question, and we resist the urge to mistake mystery for evidence of the extraordinary. Because the universe is full of mysteries, and most of them, when solved, reveal the beauty and complexity of natural processes we didn't fully understand. But some mysteries, perhaps one day, will reveal something else entirely. And if that day comes, if 3i Atlas or another object proves to be the confirmation we've been seeking for decades, we'll need to be ready, not with panic or denial, but with curiosity, courage, and the recognition that our story is larger than we imagined. So here we are, October 24th, 2025, 5 days after the trajectory deviation was first detected, 5 days before perihelion observations become available, and 30 days before the IAWN monitoring campaign begins in earnest. The data we have raises questions that defy easy answers. The observations coming in November and December will either resolve those questions or deepen the mystery further. This is science in real time. Messy, uncertain, debated, and absolutely fascinating. If you want to track this story as it develops, subscribe and hit notifications. I'll be covering every major observation, every updated trajectory calculation, and every peer-reviewed paper that comes out of this campaign. I'll be watching the November 3rd reacquisition, the Keck spectroscopy results, the VLT organic molecule searches, and whether that trajectory deviation holds up under rigorous scrutiny. And if the extraordinary happens, if somehow this object proves to be something beyond natural explanation, we'll explore those implications together, carefully, honestly, and with the skepticism that good science demands. Drop a comment with your take. Natural comet with unusual properties, or something we need to take more seriously. And tell me what evidence would convince you either way. What would it take for you to conclude this is artificial? What would it take to convince you it's definitely natural? Those are the questions worth asking, because they reveal how we think about evidence, how we balance skepticism with openness, and how we navigate the space between what we know and what we hope might be true. Let's figure this out together. Thanks for watching.